You working?
Yeah, you see me?
You will get that.
No?
Now, students, it's just not the same.
Hopefully this will work.
Students are like, well, that was an easy.
Yeah, and it says it changed to red that stop broadcast.
Oh.
Maybe I can put a board there.
Wait, in the middle of that?
Oh, you can see me? Okay, okay. So we can see the
That's good.
Anybody has
you can see the screen.
Well, you did this, you what you wanted. Sometimes you have to do that. I wanted for a very long
I don't want to
time
touch
to anybody.
here.
I wanted it.
No. This is right now it's a blue because we don't know how to do it.
Well, they don't have
Yeah.
some also like
We haven't seen one.
Yeah. Black and Saturday.
Yes.
Where goes black? No. That one was work. It worked for like 2 minutes. And then we decided to
I can
not
log
work.
it.
Yeah. But now you can't.
And they-
I can't take
It says to press the help button, but there's no help button.
Well, if, I'm just gonna get the equipment.
No idea. No, we need to sort
Wow.
the install.
It's not what, he's been working on it for now, I don't know how long. But he's got 7 minutes, there's no problem. Where do you want to sit? In the back? Who's in the back? This is David's old lady, I sit up there. Sit right up here. Okay, all right, okay.
Oh, really?
I looked at you.
Oh, hello.
Hard.
You should have asked me.
Alas, I acknowledge mistakes, and I was like,
You already what? I did.
I turned it off and I turned it on again. You can turn it off.
Is it working?
Oh, well.
Yeah.
Right, he turned it off.
Oh, you turned off the projector?
Yes.
It is now.
If it doesn't work, just turn it off and then turn it on, right? Oh, that'd be better. Just, can everyone grab around my laptop?
Yeah, that's what I want to say.
Yeah, but wait, it's off, so it doesn't make sense. Okay, yeah, that's great. What did you do? Okay. Okay, so we have a through around. Guys, switch it up. Switch it up. Okay.
It's not working, so that all of them, and I can't get it going?
I know. And like, how many people with doctorates can't figure this thing out?
Yeah.
Yeah, I mean, that's last thing.
Wow.
This might.
Clear settings.
Now we can.
You,
when you first.
Oh, man.
You didn't wait long.
Well, it's almost 1, so I'm gonna go up to the admin's office and ask for help.
I'm back.
Yeah.
Just wait a second.
I'm not gonna walk very fast, so I don't break into a sweat.
Light is going. Yeah. It's here.
Open the screen.
Okay.
We can make it work.
Okay.
Now it
Sources. What are you doing?
What is sourcing?
Laptop, doesn't matter. Mac is this company. Laptop. Big screen. And what do you need to do Mac to pull the screen?
Wait, now?
I'm just reconnecting it. It usually doesn't work if you just.
But I mean, is it HTTP?
What is it saying?
Okay, it's,
Yeah, but
Try everything.
should talk
You can just delete
so
it.
much that it cannot be served. It's not press all the time.
let's press the button around.
Let's close the presentation and it's
What happens to some sort of common law but it's still fine at the number of segments. Fundamentally, yeah, it's like you think that if you take two slice, so if you take a projector and there's another pieces, projecting
Yeah, I think.
I'm not the first to use this, but I get.
No, that's what happens when you try to use Windows. So you
Where is this?
and the other side. I'm sure someone used Windows at some point and then they broke it.
Oh, yeah, I think the base himself.
Yeah, he's trying.
I think he was.
Oh yeah. Windows 9.
No, it makes sense.
I think it looks good. Yeah, just we don't have the slide yet, so I don't know. It's fine. It's our channel away. Yeah, she.
I don't know
I don't know why.
You know, this is the thing. It doesn't even detect this thing. That's the problem. No, we have the. Oh, yes.
Don't worry, guys. You'll get sorted out.
Okay.
Thank you.
She was.
I haven't decided yet.
How she.
Oh, okay.
So that's the live stream.
Yes.
My friends watching.
Oh, really?
No, but they will. If not, then.
In contact with Lewis. Okay. Because there's a formal procedure where Lewis, he can sign for Lewis.
Oh,
Lewis passes him the question directly to the CD.
Okay.
Right. That's our question. So there's,
So it's all working out.
I think either way is fine, but we can have.
Well, we also have to wait for technical support as well.
No.
Hi, how are you? Very well, thanks.
You're very serious, man.
Right? I have to. Somebody told me I should.
This is the little
It looks great. Thank you so much. That's sweet. Now I can do my presentation.
Yeah, I saw him on Broadway in the usual way where he was in his own world. I walked right by, I tried to do this. Yes. And the song, the what about?
Yeah. Sure, yeah. I think so.
I'll see if I have it.
I mean, also, I don't know if there's.
It's there. It's being put there.
No, I think she's calling, Spencer for me, that's not my number, it's not working.
Well, it seems to be working. That's because it's being.
Here, what's there, I'll call for you, what's his extension?
I
Get an email. Does anyone know Friesner's extension? 4 dash what? That's not true.
Yes.
Ah, good. Good call.
We disconnected, reconnected again, turned it off, again.
So we visited.
It's not.
So take down here.
It worked like a minute, and then. The nice thing is that we're nice one. So, but.
I talked about that yesterday, she said she was going to try, and
Yeah. So I think we're gonna go out there. Glad happy.
Not far.
We didn't know. Yeah, it was. Well, this wasn't. Yeah. It's better.
It doesn't seem to be a problem.
Oh, yeah.
But sometimes monitor is not or computer is not. The computer is well. Thank you so much.
I've never been to I guess you.
Yeah.
Thank you so much. Thank you so much.
I want you to be able to talk.
Yeah, but I think those are somehow encapsulated that. Well, no, this is his. It has a, it's in what's here. But it's here. No, it's short. No, it's just not. In fact, they'll buy it.
It must be something with the director. It was working. And the other
It was working as a.
earlier today, yeah.
Oh, earlier today.
Yeah.
Just. I mean, now it just says, 6 minutes, so right.
No, we have another, okay, so maybe we can.
Well, the middle one
Is it? They just won't have access to the table. Yeah, there's. No, it's just, thank you. Yeah. I wasn't, if I wasn't nervous before. Yeah, it's given me some time to not be nervous. Well, it hadn't happened until now. Oh, good. I didn't leave without getting my fair share. Are you going to? I don't want to see it. Yeah.
We're at the same
Since we're 20 minutes late, I'll be very brief. I want to say two things. One is just what the ground rules.
Let's not plug the computer in. Okay.
Very quickly, Andres will talk for 45 minutes. There'll be no questions during the presentation. Afterwards, any of you can ask questions. None of the committee will ask questions. And then we'll ask everyone who's not on the committee to leave, and then the committee's questions will be asked. Second thing I want to say is much more fun, which is how proud I am of Andres, who's standing here looking so dapper. A few things about Andres as a graduate student. I think it took about 3-point-something years for us to click together as a mentor-student team. There was a lot of false starts and difficulties, and then all his doing, it was like a light switch that went off, and he's written 6 papers in the last 2 years, which is remarkable, and they're great papers. In fact, one of them's not even in his thesis. That's how confident he is about, not having to show everything that he's done. But he's always been and always had been very, very gifted and talented analytically. Like all graduate students, he had some weaker facets of his repertoire. All of those things, including, Andres is a very literate person, but his scientific writing style wasn't my scientific writing style. So I don't know if he's a better writer now, but he writes in the way I like. So everything now is really amazing, to the point where I think he has a tremendously promising future in science, and I can really honestly say he's one of the handful of excellent students that I've had in my group, and I'm very, very proud of him. So today he's going to tell you about approximate but accurate dynamics of complex systems, getting more for less.
Thank you very much, Dave. Thank you for that wonderful introduction. It was great.
I don't want to press any buttons.
I don't want to do anything.
All right, let's leave the lights on.
Yes, everyone is okay with that. But yeah, I hope that I can live up to these words in this presentation. So then I'll start. Today I want to introduce you to some simple yet accurate ways of calculating the quantum dynamics of complex systems using generalized quantum master equations. But what are generalized quantum master equations? They're just simple equations of motion for a dynamical observable that you care about, say a non-equilibrium average or an equilibrium time correlation function. And it exists in a reduced dimensionality. Let me unpack that a little. Imagine that you care about the position and momentum of this big particle, which is swimming in a fluid of much lighter and smaller particles. Here, you might have potentially an infinite system. There are many of these little particles. And if you want to track the position of this guy, then you really should care about the motion of the little particles bumping into it. And soon, keeping track of all the motions in the system becomes quite hard. But the correlation function, or rather the dynamical quantity that we care about, is at most 6-dimensional. 3 position coordinates and 3 momentum coordinates. And so our generalized quantum master equation will be at most a 6 by 6 dimensional quantity. A huge reduction in the complexity that we had initially. Now that is not to say that all of those other degrees of freedom, the little particles moving, are out of the picture. No, they influence the motion of the particle. They just come into the equation through this memory kernel. And yes, the memory kernel is very difficult to calculate. And if you solve it exactly, it amounts to solving the problem in full, the original problem. And for the rest of this talk, I want to introduce you to some simple, but hopefully very accurate representations of this memory kernel. But before I go into the main body of my talk, I would first like to motivate the use of generalized quantum and classical master equations with some cases where they've already worked very well. The first example that I want to cite is that of liquids, supercooled liquids, and gases. The dynamics of these systems can be very complicated, but we're often interested in a simple macroscopic observable, say the diffusion constant, or the viscosity coefficient, which can be expressed in terms of equilibrium time correlation functions. One such equilibrium time correlation function that reveals much about the structure and dynamics of the liquid and its supercooled counterparts is the self-intermediate scattering function. It is simply a density-density correlation function at equilibrium for this system, corresponding to some inverse length scale k. You can measure this quantity using light or neutron scattering experiments. And here, I'm showing you the behavior of this correlation function for a liquid at high temperature and low pressures. Initially, we have holistic relaxation followed by some exponential decay. That's very simple. When we start cooling down the system or increasing the pressure, we start to see the emergence of more complicated relaxation patterns. For example, we see the emergence of the beta relaxation regime, where particles are stuck in cages of their neighbors, who are similarly immobile. This region can last for a very long time. Note the logarithmic time scale here. And eventually, maybe the particles can escape their cages and enter the alpha relaxation regime, which is characterized by stretched exponential behavior. Generalized classical master equations have already been very useful in exploring some of these relaxation patterns, especially when you use the mode coupling approximation. These studies have shed light on the nature of the glass transition. Again, I want to emphasize before we move away from this slide that we have a very complicated system, but we're really interested in a seemingly simple dynamical quantity that is not really tracking all of the degrees of freedom in our system. It's just looking at a few of them. The next problem that I want to tell you about comes from out of equilibrium physics, a nanojunction. Imagine that we have two leads, and in between them, we set up a molecule or a quantum dot, and then we set up a potential difference between the two leads. We're going to get a current going through this nanojunction. Here, what we're interested in is the current as a function of the voltage difference and also of time once you make your nanojunction. But of course, you should really care about a lot of things. For example, the detailed electronic structure of this molecule. How many electrons are there? How are they interacting? How is the molecule vibrating? And maybe what are its forces? And how do these things couple to the electronic degrees of freedom? We should also maybe care about the microscopic state of the leads. But in fact, the correlation function that we care about, or in this case, a non-equilibrium average, is a very simple quantity. We're just tracking the current as a function of time and voltage. And so again, generalized quantum master equations in this case have played a large role in explaining some of the phenomenology that we see, especially when you make use of perturbation theory or other more sophisticated techniques. The final example that I want to tell you about is excitation dynamics in molecular systems. And here I'm showing you the prototypical example of the Fanda-Matthews-Olsen complex, the FMO complex, which consists of 7 chromophores embedded in a protein environment. In 2007, some experiments showed that you could get long-lasting quantum coherence even at room temperature. What am I doing here? I'm shining some light on chromophore number 1, and I'm exciting it. Then I'm watching how the excitation moves through all the other chromophores and how the communication with the system results in dissipation and decoherence. So again, in this case, generalized quantum master equations, whether through the use of hierarchical equations of motion or perturbation theory, have yielded very important results to elucidate the physics here. Now that I've given you these 3 examples, let me just look in more detail at the type of correlation function or non-equilibrium average that I'll be interested in. And just to be very explicit, I can rewrite this correlation function as the inner product of some vector A with itself at time t. And just expanding that notation, it's just a trace over some operator that often has unit trace, and some component of this vector A at time 0, and some component of the vector A at time t. We can always interpret the multiplication of these 2 operators as some generalized non-equilibrium initial condition. Now let's see how that translates into the 3 problems that I showed you before. The first one you'd already seen is just a density-density correlation function corresponding to some inverse length scale k, where this operator O becomes our canonical distribution. And these 2 operators, the 2 components of A, are just density modes. In the case of the nanojunction, we have these 2 operators, gamma L for the left lead, and gamma R for the right lead, which tell us the state of these leads as we start the measurement. Then the initial population, let's say of 1 electron pointing up, 1 electron pointing down in the molecule, and we're going to track the population as a function of time of the electrons going through this nanojunction. If we now take the time derivative, we get the current. And finally, in the case of excitation dynamics in molecular systems, we have the initial condition for our protein scaffold contained in this gamma B. And we have the initial excitation on chromophore 1, and we're going to track the population on chromophore 1 at all subsequent times. So all of these very different examples conform to this type of generalized correlation function, let's call it, for the dynamical quantity that we care about. Let me now introduce you to the simplest possible system that exhibits much of this physics. And I know that a lot of you are already familiar with the spin boson model, but bear with me. It consists of two sites characterized by different energies, epsilon and minus epsilon. So now the difference in energy is just 2 epsilon. And they see each other electronically through the non-adiabatic coupling. And these guys are embedded in a bath of harmonic oscillators. Of course, if our system, our subsystem consisting of the two sites, does not interact with our bath, this becomes more or less a boring problem, right? Something that we can solve very easily. So let's have some coupling. And we could always expand this coupling as a function of the positions and momentum of the harmonic oscillators. I'm going to take the simplest possible expansion, cut it off at linear order, and I'm going to take the opposite for the other side. Just to give you some intuition, if I have an excitation that is staying on site 1, the harmonic oscillators are going to reorganize around that excitation and lend it some stabilization energy lambda that will further localize it. If I'm on the other side, the opposite thing happens. Now let's see the mathematical formulation very simply of this Hamiltonian. In the diagonals, we have the energies. The off diagonals have the diabatic couplings. And then we also have the interaction between the system and the bath. And we could always interpret this from the usual Marcus picture, where the two sites are the base of these two parabolas. The parabolas indicate the harmonic oscillators. And we have also the coupling between the system and the bath, which you can interpret as coming from a Frank-Condon transition directly up to this harmonic oscillator and the dissipation of all that energy as you come to the base of the next oscillator. For the next couple of slides, I will be focusing on the following dynamical quantity: the population difference between the two sites as a function of time, given that I've initially excited site 1. So now we're going to see two slides that are more or less full of math, but just bear with me. This is the correlation function that we care about, and to be very explicit, to bring in this dependence in time, we're going to have to act with the propagator. Now let me introduce two projection operators that are very important. The projector P, which projects onto the subspace of A, the quantities that we care about, and the complementary projector Q, which is orthogonal to P, that is P times Q is 0. Let's now write down the equation of motion for C, which just requires that we take the time derivative, we bring down the Liouvillean, and bring in a 1. This allows us to get two terms. And if we bring in the definition of P here, you'll see that we get A e to the ALT A, which is just the original correlation function. And here, we're going to expand this propagator using the Dyson equation. So we're going to get 3 terms now. As promised, the first one has the original correlation function. The second one looks ugly, but is actually 0. I'll show you why. And the third one looks like A e to the ALT minus tau, A, which looks a lot like that. So we have CFT minus tau, and something that looks ugly. I'm going to call that the memory kernel. This thing is 0 because when we expand this as a Taylor series, I will always have a Q touching A. And A is part of P, and Q times P is 0. So this is the generalized quantum master equation, and you've derived it for the first or 111th time. Congratulations. Now, let me give you some intuition for how this all works out. If we, again, look at the spin boson model, the two-site system coupled to the bath of harmonic oscillators, and we turn off the memory kernel, and in the projector we include all of the states for the central spin, we will only have Rabi oscillations. We excite on site 1, and the excitation just move coherently between the two sites. If now we turn on the memory kernel, what we're going to see is dissipation and decoherence. Great. Let's get a little bit more intuition for the memory kernel. It looks ugly, especially because it has this Q up here in the propagator. That is called the projected propagator. And a lot of treatments have just ignored that Q. They set it to 1, and they go from there. But what we're going to do is use the Dyson equation to unpack this equation again. And we're going to get a self-consistent relation for the memory kernel, which is very difficult to calculate. And now we have these two auxiliary functions, which I'm going to call the auxiliary kernels, and these are their forms. Now, if you remember, C of t was a e to the ILT a, and I said this is very difficult to calculate. We need to come up with something simpler. Now I'm asking you to calculate these auxiliary kernels, which have a bunch of stuff, e to the ILT a. These are just as hard. Where is the benefit? I hope to convince you that there is some benefit. So in 2003, Shi and Yeva decided to use this trick to calculate the population difference between the two sites as a function of time. And they used a very expensive numerically exact method. And here is that population as a function of time. As you can see, the population decays by a time scale of 15. And if you solve the memory kernel also exactly using the same expensive method, you can recover the exact result. That's great. But this is the interesting part. Look at the memory kernels. They decay on a time scale of 1.5 to 2. That means that we only need to calculate the memory kernels up to here, and we get the rest of the dynamics effectively for free. Now remember that numerically exact methods are very expensive. So this represents an incredible boost in efficiency. And people, of course, realized that this was a good idea, and they hopped on the bandwagon, and they decided to use this method, not only to calculate the population dynamics in this Conboson model, but also in more complicated systems. But then you could ask the question, instead of using this very expensive and difficult to implement numerically exact method, can I use something cheaper, something simpler to implement, an approximate method? So that's precisely what Shi and David did in 2004, but then later the Markland group in 2013 with the momentum jump solution to the quantum classical Euclid equation. This is also a very expensive method and becomes unstable when you try to calculate the population dynamics directly after this point. As you can see, the error becomes crazy. The black dots are just the exact result, and the green result is what you get when you solve for the memory kernel using the approximate method, and then use those memory kernels to get the evolution for the population dynamics. Effectively, you're getting all of this dynamics for free. And then you could ask the question, well, this is still a very expensive method. Can you do something with a cheaper method, something a little rougher, like the Aaron test method? Here you see the result in the dashed line for the direct Aaron test method. The black dots are the exact result, and the solid blue line is the result that you get from calculating the memory kernels using the Aaron test method. As you can see, this generalized quantum master equation approach, GQME for short, will get us to what looks like the numerically exact solution. And this is great, and a bunch of people also recognized that this was a good thing and hopped on the bandwagon and started calculating things. But there remain some fundamental questions. And these include, well, I've told you that the benefits in efficiency rely on the short-lived nature of the memory kernels. Are we always sure to get short-lived memory kernels? The next thing is, well, can we always be certain that we'll get improvements in accuracy? They look great for the approximate methods. And the final thing is, what mechanism leads to these improvements when you use semi-classical methods, which are approximate, to get the memory kernels? To answer these questions, I'm going to focus again on the Aaron test method, precisely because it's so simple. Now let me give you some intuition about it. It's an approximate method. It's mean field in nature, which means that it cannot deal with correlation very well. And it also treats the path classically. There are problems because of these assumptions. For example, the fact that we cannot deal with strong correlation means that we cannot go to regions of large coupling between the system and the bath. It also means that because we have a classical bath, we cannot access very low temperatures or bath frequencies that are very large. And finally, because of the classical treatment of the bath in connection with the quantum treatment of the subsystem, we're going to break detailed balance. And you'll see that this is a big problem. But there are virtues to the method. First of all, it's very easy to implement. The second thing is that it's exact at time 0, and there should be an asterisk here, and I'll tell you why later. And it's short time accurate. Now let me show you some of the dynamics that you can calculate with the error test method. The black line is the numerically exact result, and the green line is the direct error test result. As you can see, it consistently leads us to the wrong long time limit, precisely because of that detailed balance problem. It can also lead to overly fast or overly slow decoherence. So now I'm going to try to answer the first question that I posed, which is, will we always get these short-lived memory kernels? And one thing that you should keep in mind is that the parameters in your system determine the lifetime of the memory kernel as much as something else, the projection operators. So here I'm showing you the Redfield type projection operator that contains both states, site 1 and site 2 in our two-level system, but also the states that take us from site 1 to site 2 and from 2 to 1. And if you calculate the memory kernels, they look short-lived. They end at time 2, and they look well-behaved. Now what happens if I get rid of the coherences, these states that take us from 1 to 2 and from 2 to 1? That I'm going to call the NEBA type memory kernel. And now these memory kernels are much longer lived. They die only when they get to 20. Now, in the literature, there had been this thought that much of the improvement that you get from this method is that you get these short time accurate dynamics that give you very short time accurate memory kernels. So if you buy into that idea, you have to say that the Redfield type memory kernel is going to give me better dynamics than the NEBA type memory kernel. But here are the dynamics. They both yield, effectively, the numerically exact solution to within graphical accuracy. This tells us something very important. The accuracy boost is not dependent on the short time accuracy of the semi-classical methods. Now let me try to answer the second question that I posed, which was, will we always get, oh, before I go there, sorry, let me show you some examples that this is actually a robust result, and it works for a lot of regions of the spin boson model. Now let me try to answer that second question, which is, will we always get such incredible improvements? And to do that, I have to introduce what are called closures. And that comes from different ways of writing the auxiliary kernels. Let me point out first that if you're using a numerically exact method, you will get the same result, the exact result, regardless of the closure that you use. But because we're using an approximate method, this is not necessarily the case. Let me focus now on the action of these operators, QL acting on A, and the bra, in this case, the generalized bra. What those operators do is rotate that vector A and push it out of its original space. Now we're going to act the propagator on the vector to the right, not the one to the left. This distinction seems silly, but it actually becomes important later. And if I do that directly, if I calculate this quantity directly, that is what I call the CB0 closure. What I'm going to do now is play a little game. I'm going to use the definition of Q, and I'm going to expand in terms of these two terms. I'm going to see this Liouvillean down here, and I'm going to get rid of it by taking a time derivative, so that I can re-express the second closure this way. It's important to note that I've gotten rid of the L that acts on the A that is going to be dynamically sampled. The next one is playing the same game, but with the static Q. This allows us to rewrite it and get our CB2 closure. And then the final one, I'm just going to play the same game twice. Now, I have to repeat myself. If you use numerically exact methods, you will get the same answer for all of them. But this is not necessarily true for approximate methods. Let's see what the results are. These are the results that I showed you before. They look great. Again, the error test method gives me the green line. The dashed red line is the result from the generalized quantum answer equation, and the black line is the numerically exact result. Great results, right? It corrects it. If I use this closure, I again get these wonderful results. When I use the next closure, I seem to break the method. In fact, I'm recovering something that looks an awful lot like the original Ehrenfest result. And because doing this didn't matter, and because doing this mattered, I would expect that this guy will give me the same result as that one. And it does. And in fact, we also proved analytically that when you use this closure, which allows you to write the auxiliary kernels in terms of the original correlation function and its time derivatives, you are sure to get the original dynamics that you started with, whether it was exact or approximate. And then we also outlined the characteristics that a method has to have in order to recover the same result as this closure. Now, that does not explain the source of the improvement. And this was done in collaboration with the Markman group. Let me try to answer that final question. Where does that improvement come from? As you saw, it was the static part of our auxiliary kernel that seemed to have the secret to this improvement. So let's take a closer look. Within the semi-classics, this is treated in a special way. Let me just remind you what the results look like. They look good. And this is what the semi-classical treatment entails. You need to take what is called a Wigner transform, which I will introduce in a little more detail later, of this product of operators, which gives me the operators, Wigner transform, and a correction term. And what I'm going to do is turn off this correction term to show you that that matters. If I do that, I break the method. Of course, this is not proof that this is the source of the improvement, but it certainly points the way to saying, yes, this matters a lot. Now, so far, I have shown you how to calculate non-equilibrium averages. Can we do something a little harder? Can we calculate equilibrium time correlation functions? Before I show you that, we have to look under the hood of the Ehrenfest method a little more. And before, what we were calculating were these averages, which required the Wigner transform, which is just putting in phase space the operators for the bath, and then treating them classically. This was simple because this is an easy operator. This has been known for many decades. But when you have the equilibrium time correlation function, we have an important distinction. This is not just e to the negative beta h of the bath, the Hamiltonian of the bath. This contains all of the components of the Hamiltonian. And this becomes far more difficult. So I decided to get a semi-analytical expression for this. This is what that Wigner transform looks like. It requires a Fourier transform of this quantity, which is just the off-diagonal element of the Boltzmann factor. Let me interpret this from a path integral perspective. It is simply the overlap of this final state with this initial state after I've evolved at an imaginary time. But of course, getting these paths without any approximation is virtually impossible. So what we need to do is use an approximation, and I use the simplest one that I could think of. I just chopped up this Hamiltonian into little pieces. But that approximation becomes bad the longer the path is. So what I can do is chop up the path into little pieces so the approximation doesn't become so bad. And of course, when I introduce these slices, I have to pay for it by doing more integrations. But I can do that, it's okay. And I did, and the results were pretty nice. First of all, doing this has several advantages. One, you can converge to the numerically exact result by including more and more path integral slices. The second thing is that the expression that you get is very easy to sample on the computer and allows you to calculate any thermodynamic quantity that you want very simply. Here is an example. What I'm calculating is the difference in the population between site 1 and site 2 in equilibrium. This is the polarization. And here I'm varying the inverse temperature. And I'm also varying the bias that I'm applying to the two sites, the energy difference between the two sites, the speed with which the bath reacts to the central system, and also the coupling between the system and the bath. And this not only reveals the potential for this approach, but also tells us something really neat. about polaron physics that we already knew. For example, the greater the bias, the more likely we are to form a polaron, right? We see that this line is the one that gets closest to -1. The faster the bath, the easier the bath can reorganize to stabilize our polaron. And the stronger the system-bath interaction, the stronger the stabilization of this polaron. Another important thing, which was the initial motivation for doing this project, was that we can use the Wigner transform, the thermal Wigner distribution, to sample the initial state exactly for equilibrium time correlation functions. And it can have important consequences in the dynamics that you calculate. For example, this case is not very interesting, but it shows you the convergence with increasing number of path integral slices. But this case is the most interesting, really. As you can see, when we go up to 6 path integral slices, we're getting the result that most closely resembles the exact result. And it recovers the exact dynamics for far longer times. Finally, this is a useful thing for benchmarking approximate methods that are being implemented now and that continue to be developed in the future. So now I'm going to use this to show you that the generalized quantum master equation approach, which adds that extra layer of benefit, can also help us in the equilibrium case. And these are some results. In the case where the Ehrenfest method is already quite good, we recover the same result. But in cases where the Ehrenfest method fails, we recover much better results. So indeed, it works. Now let me go back to that question that I posed earlier. Where does the improvement come from? As I said, it relies heavily on the sampling of zero-time operators, right? That operator that remains static, the one that we did not evolve, was super important. In the non-equilibrium case, I showed you that you get this main term and a correction term. In the equilibrium case, now we have that full density operator, for which we required that approach, the Wigner approach that I just showed you. In this case, first let's look at this panel, which is the direct Ehrenfest result. In some cases, regardless of how many path integral slices you include, the Ehrenfest result will still not look great. But when you add the GQME stuff on top, it can correct the dynamics. But not only that, that correction is sensitively dependent on accurately rendering that Wigner thermal density. And with that, I want to summarize what I've shown you so far and conclude. I hope that I've shown you that the memory lifetime not only depends on the parameters of your system, but also on your choice of projection operator. I've shown you the boosts in efficiency that the GQME approach can afford. And I've also shown you the improvements in accuracy that are possible when you use semi-classical methods to calculate the auxiliary kernels. These are the results again. And finally, something that is not easy to emphasize during the presentation, but which was true nonetheless, is that in our approach, we unified the Mori and Nakajima responsive formalisms into one, which allows you to treat both in and out of equilibrium processes, time correlation functions and non-equilibrium averages, and you can also generalize to multi-time equilibrium correlation functions. And with that, I want to thank you. And before I end, like for good, I want to acknowledge you. First, I have to thank Dave. He has been an amazing advisor. He has given me all the freedom that I've needed to explore the things I like, and he hasn't pressured me to do anything that I don't like, which is just as important. I also have to thank him for letting me become an independent scientist. His attitudes towards science have informed my approach to science, and I think now I can recognize questions that are interesting, that are worth tackling, and I have some insight into how to tackle them. And finally, I have to thank his generosity, because without his work, I wouldn't have been able to do my PhD at Columbia. When I applied, I was in a difficult immigration situation, and he helped immensely so that I could come and do my PhD here. I also have to thank my committee members, one of whom, unfortunately, was not able to come because he's ill. I wanted to thank Rich for giving me all these very insightful questions that pointed me to the practicality of my approaches. I have to thank Louis Bruce for pointing me to the questions that are of interest to experimentalists and how to present my work better. I have to thank Sadiq because he's been with me since undergrad and he introduced me to theoretical chemistry and he's provided me with the much needed support, both intellectually and personally, that I've needed throughout the years. And finally, I want to thank Bruce Byrne, who I read as an undergraduate student and made me love time-dependent statistical mechanics. And he is both a great teacher and a great source of inspiration. I also have to thank my group. They've been amazing. Theta has been an awesome friend for a really long time. Everyone in the group has been awesome. We've had some amazing postdocs. And the past members of the group have also been super helpful in my growth as a scientist. And I cannot forget our furry friends who have been with us over the years. Ruby, Hickory, and Matt. They've all made our stay in the Reichman group very happy. I have to thank the awesome friends that I've had at Columbia. They've been true colleagues and great friends. And finally, I have to thank my family. Bonnie and Joel, my mom, my dad, my sister, my brother, my husband, my aunt. They're all here, or at least in spirit, most of them. And I thank them all. Without them, I wouldn't have been able to do this. Thank you.
Okay, question time. Are there any questions?
So for systems where the memory decays quickly,
Is accurate or useful or what?
both.
Both.
So is there anything you can learn about calculus? And it's also easy to calculate the memory at short time.
Yes.
Is there anything you can learn about calculating memory for those systems that you can apply to systems where the memory doesn't decay?
Yes, so that's an active project, and it's looking at the memory kernels that you would get in spin chains. And the way that we're approaching this is with a numerically exact method, the MRG, that's the matrix normalization group method. And the main problem here is that because the memory is long-lived, you really have to come up with better ways of writing down a projector. Because if the hope is that if you write down the correct projector, then you're probing the correct dynamic quantity, the memory kernel will be short-lived, or at least will have a finite lifetime. Of course, there may be problems where the memory kernel has an infinite lifetime, and in those cases, I don't think this approach would be very useful.
As at the beginning, you made 2 or 3 experimental systems that serve as motivation for developing these tools. Can you comment a little bit on how this formalism is now being applied to study the dynamics and maybe some of these, because all of them, I think, are things that are studied here.
Right, yes. So the nice thing is that so far, most of the studies that I've done have to do with model systems, very simple physics models that give us insight into how the method works and when it breaks down. But it's also been applied to look at electron transfer in realistic systems where the solvent is atomistic. And in that case, it has proven to be very useful in that it improves the accuracy of the method, and it also allows you to study these dynamics for longer times. It has not yet been applied to the nanojunctions, but that's something that I'm actively pursuing now. And in the case of the excitation dynamics, it is currently being applied to the ethanol complex, again, as a model system to see if it works there. And the next step is to add an atomistic bath for the ethanol complex.
Yeah, I think the nanojunction work in particular could be really useful because there's so much data on, slightly different molecules
Right.
in the junctions, and so this would be a good way to go back between the experimental and the theoretical.
Yes, exactly. That was an awesome question. And I would just like to add that in the case of the nanojunction, I think it might also be interesting to see what would be the minimal model for the nanojunction, for that central system, that would be sufficient to explain those physics. Yes, or?
So if I understand correct, you see like when you use generalized modeling approach. But to the answer, where does the improvement comes from? It's still in the range, right? You can compare it with this term and with the term, sure,
In the,
so it matters.
yes, in the non-equilibrium case, I wanted to show a suggestive result where turning off that term clearly breaks the method. And the way that I see it is that you are probing some system bath operators at time 0, and you're sampling them exactly, which now biases the correlation functions that you're calculating so that your memory kernels become more accurate. I tried to follow up this non-proof, this just suggestive example, with the equilibrium case, where you would assume that if the time 0 data were not important, then any random or not any random approximation, but any crude approximation to the Wigner thermal density would still give us some improvements. But what I hope to show in the last couple of slides was that you need to accurately render, exactly render the Wigner distribution in order to get the improvements that you saw. So yes, it was not a proof, but I hope that it's very suggestive that the success of the approach when you use semi-classical and quasi-classical methods relies heavily on the accurate sampling at time 0 of these system bath operators.
Would it be easy to really know it down for?
I'm not sure. I think that's an open question and maybe one that I'll have to work on for a little bit longer.
Well, if there are no further questions, let's ask these guys to stay here and everyone else to leave for a little bit.
Nice to see you. Very good. How was it?
No, actually, it's different, so I don't know.
Oh, okay, okay.
Yeah. Where will you? I'll get the key for the other room.
So I will put you here.
We can walk.
We can walk. Okay. Me esperas de acá. Me esperas lo estoy. Okay.
Okay.
Yeah.
Okay, now.
How are you?
Okay.
Working hard?
No, I don't know my hands. Are you guys?
I don't know if there is something. Oh,
How are you? Say
Hi, how are you?
Sorry.
No, hi. Hi.
Can you take them?
Yeah.
I can take you actually now because I have to go by the restroom.
It's okay, you can.
Do you want to? Is it done? No, it's still live.
Still live. Wait, why are you closing? Where is it closest?
I think they're going to talk first.
Really?
Yeah.
Okay, I'll get the key and then you can go to the restroom.
Yes. Thank you so much.
Hacerle un librito a él de copias para que los pequeños puedan leer.
Can you wait here? I'll come.
Yeah, go talk to Jay and ask him what you need to do to sign up for the safety training.
Okay, all right, I'll do that.
Because I know there's an email, but I don't have it handy.
Okay, I got you. Thanks, Danny.
You're welcome.
Hi. Can I get the little room, please? Thank you. Thank you. You're welcome. I'll bring back to you.
Oh, it looks like a jungle. I thought you love the ocean, you love water. That's right. Birthday home. We moved on the 20th.
Necesitamos.
Oh, thank you. Oh, nice. You just got I just got that. They closed them.
When we can find plates and.
Oh, really? You don't have it?
Yeah, I don't have it.
Really?
Right here around. Okay. It's okay. No, we don't need the place. We need to find the place. Yeah. Oh, okay. We have
But I'm just really so like happy chat.
Oh, that's me. Huh? Wow, let's get lunch. Yeah. Oh, there you go. She's in Canada. She's working. Are you moving to Rhode Island? Are you moving already? Where are you at?
Yeah.
Are you working? I'm working.
Are you working?
I am working. I retired from my job. But, it's just what I can properly. We have research.
And then you drive out.
Yeah.
Does anyone know where others went? They called to take a little break and we can't have it.
I told you went back upstairs. I mean, out there, but yeah. Oh, long time ago. That was.
So we worked there. Well, I was there for a long time.
But it was in the same place, right?
Yeah, where you
What are you doing now?
I went to Humana, it's another health insurance, so contracting.
What does that mean?
So we do contracting with hospitals, that's what I do.
Oh, you make it happen.
Like the contracts every 6 terms.
So why are prices so high? Never mind.
Because
Everything's so expensive.
it's for you, and there's overutilization.
$80 aspirin. I saw that thing, there's a story of epinephrine, you know, that they're these pills, these things for allergies, they're like $600 for one, right? And so kids are not getting them because they're being frustrated. They can't afford it. It's crazy. And they're generic, somebody should have.
And it's just a huge difference from, even like, your employers most of the time cover part of your health insurance, right?
Yeah.
When you're most of the time patient. So when I worked at health first, I'm just gonna give you an example of how expensive it can be. The insurance that I had there for my acne medication, I only had to pay like $50 when I used it. Now with this insurance company, my coverage, I have to pay $300 if I need to still have the same acne
I just
medication.
had the same situation because I had to take two other medications that the insurance paid for, but they didn't work over the time. So I had this new thing, $350 a month. They won't cover it all. They refuse it. Right, so I said, wait a minute, this doesn't make any sense. You don't pay for it. And the ones that are cheaper and don't work, you need them.
And look, I have to get it from my company's pharmacy because I have the company's health insurance. I have Humana, that's the insurance.
I don't know which medication.
Oh, I can't remember the name. But then it's just for acne. And then I said, okay, why if I go and get it at one of these retail pharmacies? Oh, $600. I'm like, well, are they going to cover anything? Oh, they would cover like 50%. Okay.
So we want this one. It's crazy. It's crazy.
Yeah, it's just,
It's getting worse.
it's not like regulated, it's just,
Yeah, I
they're
mean,
bothering you.
you get these stories when the medications, it's $300 now. What if the next year they decide to make $30,000? Your house, sign over your house, will give you medication you can live. You know, it's like, it's crazy. It's criminal, actually.
Yes, I think it is, because people should have access to are reading their medications. And something like, that is affordable. It's either you eat or you go to the doctor and pay the bills or have a surgery that you may need straight to. For a lot of people, it's just. Do they still allow people to get medications?
It's illegal.
Because I thought they stopped that when people said do it.
Yeah, but, there are medications here you have to get by prescription that are really expensive, but are not, don't require prescriptions in town. So you actually could go to town and get them because they don't need prescription.
That's like the
That's like
way in Colombia, you can get any medication without a prescription.
Right.
Anything.
Oh, that should go with them.
You can go there.
They do it perfectly.
Yep.
So is this better? You know,
The work environment is much better. It's better people.
better people.
Yeah, like the culture is different, so it helps. People are more like people, like it's not like produce, you did a finish, continue, then go home and tomorrow early. No. There's like a time where you begin and then you end. So that we like. So that company is being acquired by Aetna. Sometime soon. It was supposed to happen now, in July. That Humana was acquired by Aetna, which is the other big healthcare insurance. We don't know. It could be good, it could be bad. The reason why they're saying they're merging is because Aetna is more like commercial or family insurance, and this Humana company is more like Medicare. The two companies are national.
So they,
So this health insurance was all. So for people it's bad. For employers it's bad. For us employees, we don't know yet. Maybe good, maybe bad. Because we had the big five, and now is United, Humana, and Aetna coming together, and then they have Cigna and Blue Cross, which are coming together. So there will be not instead of five, the three big. Right? We have three big companies, and you have all little companies. Right?
that's awful. It's getting worse and worse.
And that's when you have health insurance. We don't have health insurance, you have a whole other.
And as long as Congress has health insurance that pays for everything, we don't care. That's what we don't have. So I saw a number, by 2020, healthcare will be 20% of the entire economy. So, and in 20 years, it'll be 40% of the entire, and then 80%. Then we will be nothing but that. Yeah.
Unregulated, so they can charge whatever they want.
I think so.
And now for doctors, I think they're trying to sort of prove, like Medicare is trying to make them prove how they're making their money. Like they don't want to pay per service as before. They sort of want them to get paid for the quality of service. And it's kind of complicated, but they can track it with data and stuff like that. And now, like, you know, we have like a deficit of primary care physicians overall. Doctors don't want to be doctors anymore.
No, they don't want to be that.
Because it's so difficult for them, you know, to manage the business, to make the money, and it's so expensive.
And all that
career, the liability insurance that they have to have.
And getting on the phone with the guy, I saw this happen. He calls up some kid on the other side of the line who doesn't know anything, telling him what he can do and not do. He's like, it's too crazy. Yeah, people don't want to come back, that's right. I don't know, you know, the thing is, when kids ask me what they should go into today, I have no idea. I don't know, where should anybody, where should we try? What's good for you? There's a teacher shortage now.
Yeah.
It's official now. They've asked to raise certain requirements for licensing teachers in New York. But they still keep doing that. No. Hey, oh, thank you, that's lovely.
There's not many ports, so it's my.
I use my fingers, it's perfect.
It's 8. I will be okay.
Yeah.
Oh, thank you. Are you a student here? Are you in college of Andres?
Yeah, same year.
Oh, you're in Xavier. Oh, that's so nice.
Is it physics too, or another field? Physics?
Oh, no, I'm in.
You're in what?
And in chemistry.
Okay.
Andres is physicist. I don't understand actually much today.
I don't know if I do.
Well,
What are you doing in chemistry?
Actually, I'm in the material chemistry side.
What?
Material chemistry. Material.
Materials chemistry.
Materials chemistry.
Ah, material science. New materials, clothes that charge batteries.
Something.
Yeah, okay. Yeah,
Clothes that charge batteries.
yeah.
That would be cool. So we
Yeah.
put it on
As you
our
walk, the
shelf.
clothes move, and so they generate energy. It charges your phone while you walk.
Yeah. That's a
Something
good
like that,
idea.
right?
I don't. Yeah.
Something like that. Okay. Yeah. No.
I like to.
Material science is-
Things what-
That's good. That's good. That's good. That's good. But always new things. So it's nice. So thank you for the thing. Are you going to join us in celebrating?
Yeah.
Okay. How long does it usually take?
Usually an hour. It takes an hour. So.
Oh, it's not half an hour.
That's such a cool phone. Is 6 something? Oh, that's an LG?
Oh, yeah. I like the.
I know, it's so cool.
There's still live streaming here.
Yeah, I don't know who's watching, by the way.
I guess people are off now. Only one viewer.
It shows who the viewer is.
There's one viewer. I don't know. Yeah, I don't know who that is.
So I didn't see an email address or?
Oh, there are 2 viewers now.
There are 2, okay. To be continued.
Oh,
Oh. But you cannot see who they are.
I don't know. How? Do you know? How?
No, I don't think so. Tenían que volver a reunirse con el comité en el jurado, en privado, sí, o sea, ellos allá. So you didn't go to Canada at the point?
No, I'm stuck here with kind of stuff.
How long is she gonna be gone?
Well, yeah. She just got back from Europe. She was home for 2 days and then
Oh, she went.
Macedonia, Serbia, and
Serbia, isn't it like a war zone too? Like,
she always goes to war zones. Egypt, she's in Egypt. And she was in a place right near Chechnya. You remember Chechnya, they had a war there? So she went there. That's what she does. Oh, it's a war, let me go.
and mine's will be a hot spot.
Yeah. I was quite anxious about that. Estonia is very primitive. They don't really, they barely have roads.
You have to do a defense too, or no? When you graduate.
Mine was,
Really?
that was like, it was like 3 hours running back and forth. But when they all went along in the end.
Oh, there is cake already? We got more cake.
Wow, I'm glad I didn't get a cake.
I know.
I was going to get a cake.
Too much cake.
Okay.
Too much cake is
We got, so I have some fruits and more cake. So let me go wash the fruits up and probably get it in the cake. Okay. Right?
Do you have forks or?
I got some from
Okay.
West Side.
Yes. Okay.
Everybody loves cake, right? Everybody.
Yeah.
Wow.
Wow, carrot cake. Oh my gosh, I'm gonna go sweet. Sugar rush.
Sugar rush.
We should maybe get like 3 cakes. Yay! For this celebration. There's next thing.
What's that? Who?
Yes.
Oh,
Yes.
I just retired. Yeah, I got sick when I woke up.
We did it like congratulations. Yeah, of course. Oh, really? I mean,
It's,
you're probably well age now.
I really like them, but they treat you so very. So they sent in somebody from outside of the school to do evaluation. And they rated me as the worst teacher who's ever been in the school.
Oh, wow.
Nobody's ever got it. So I said, well, I challenged it, and the principal said, no, they're going to do it. So I said, it's sick, I'm going. No, you won't go. See, oh, so you're going now.
Of course, no support. How long were you working there with that?
That's school? That's school I was. Yeah. So, very, very comfortable environment. I don't want to know what you're going Huh? No, that's another school. I love there. It was not a crazy person. It's too crazy. It's just way too awesome. And you know what it's like in the outside environment?
No, that's not right, because the only person that's not well and going to hell is you. Like, they don't care.
They absolutely.
Uh-huh.
Hey, I cannot see you.
I cannot see you too.
That's weird.
Theta,
Would you like to type?
huh?
Would you like to type?
So Theta, should I turn off the live stream? That's why it doesn't show this, maybe?
Yeah, you should turn off the live stream because I think I'm the only guy still there.
Oh, you're the one of the ones. Ah,
Yes.
okay, I'll stop broadcast.